Hello students, I am going to explain Einstein coefficients in this video. Einstein has derived two relations using his Einstein coefficients. First, he has considered two energy levels. Let E1 be the lower energy level and E2 be the upper energy level. In lower energy level E1, let N1 be the number of atoms present in that energy level and let N2 be the atoms present in the energy level E2. And he has taken rho of nu is the density of energy used for the absorption and also for stimulated emission process. So let us take rho of nu, it is the density of energy. So in the energy levels E1 and E2, when an energy of rho of nu is supplied, so absorbing this energy, the atom from energy level E1 will excite to energy level E2, and there spontaneous emission will take place and also stimulated emission will take place in the laser medium. So here we are having two types of transitions. One, the upward transition, and two, downward transition. So how the upward transition is going on? So the rate of upward transition. So upward transition means the atom going from low energy level to higher energy level. So this process is nothing but stimulated absorption. So rate of upward transition is equal to rate of stimulated absorption. So this rate of stimulated absorption depends on the number of atoms present in the first energy level, that is N1, and also the density of energy. So more the atoms present in the low energy level, more the absorption will take place, and more the energy, density of energy falling on this energy level, so more the absorption will take place. So these two are directly proportional. And in giving the proportionality constant, Einstein has used a logic that for stimulated process, he has used capital B, and for spontaneous process he has used capital A. So the rate of stimulated absorption, which is the upward transition, is equal to the proportionality constant. As this process is stimulated, so B, and the atom is going from first energy level to second energy level. So 1, 2 is the suffix. This shows that atom is going from first energy level to second energy level. Number of atoms N1 and rho of nu. So let us name this equation as 1. Now the rate of downward transition. In the downward transition, we are having two processes. One, spontaneous emission, and two, stimulated process. So the sum of these two will come under downward transition. So rate of downward transition is equal to rate of spontaneous emission plus rate of stimulated emission. So first see the rate of spontaneous emission. Rate of spontaneous emission. So this rate of spontaneous emission is directly proportional to the number of atoms present in the upper energy level. So more the atoms present in the upper energy level, there is chance of more spontaneous emission. As this spontaneous emission doesn't need any external energy, so it doesn't depend on rho of nu. The proportionality constant. So spontaneous means Einstein has used capital A, and the atom is coming from higher energy level to lower energy level, that is 2 to 1. So proportionality constant A to 1 into N2. So let us name this equation as 2. Now coming for rate of stimulated emission, this is proportional to the number of atoms present in the higher energy level, and also stimulated emission depends on the external energy rho of nu. So it depends both the density of energy and also the number of atoms. The proportionality constant is, as this is stimulated process, it is B, and the atom is coming from second energy level to first energy level. So it is 2, 1, B to 1, N2, rho of nu. So this is equation 3. So once the atoms goes to the higher energy levels, continuously they'll come down and again the absorption will take place and again spontaneous or stimulated emissions will take place. So the upward and downward transition process will take continuously, and at equilibrium, rate of upward transition is equal to rate of downward transition. So in rate of upward transition, we are having only stimulated absorption. So rate of upward transition means rate of stimulated absorption equal to, in rate of downward transition, we are having two processes, that is spontaneous emission and stimulated emission. So rate of spontaneous emission plus rate of stimulated emission. So rate of stimulated absorption means, so it is equal to, already from equation 1, we can get like B12 N1 rho of nu equal to rate of spontaneous emission. From equation 2, we can get A21 N2 plus rate of stimulated emission. From equation 3, we are getting it as B21 N1 rho of nu. So now let us bring rho of nu terms to the left hand side and remaining all to the right hand side. So B12 N1 rho of nu minus B21 N1 rho of nu equal to A21 N2. Taking rho of nu common, so we'll get B12 N1 minus B21, sorry, here it is N2. So this also N2. So B21 N2, which is equal to A21 N2. So rho of nu is equal to A21 N2 by B12 N1 minus B21 N2. Let us name this equation as 4. For this equation 4, I am dividing both numerator and denominator with N2. So this will become rho of nu is equal to, so dividing numerator with N2, we'll get N2 by N2 by, here two terms are there. So B12 N1 by N2 minus B21 N2 by N2. So which is equal to A21 by B12 N1 by N2 minus B21. So this N2 N2 got cancelled. Now again I am dividing this numerator and denominator with B21. So on dividing both numerator and denominator with B21, we'll get rho of nu is equal to A21 by B21 whole by B12 by B21 N1 by N2 minus, here this B21 by B21. This will become 1. So which is equal to A21 by B21 whole by B12 by B21 into N1 by N2 minus 1. So we got this per rho of nu. Let us name this equation as 5. So in this equation, we are having N1 by N2. And what is N1? Number of atoms present in the first energy level, and N2 is number of atoms present in the second energy level. We know that Nr is equal to N0 into e to the power of minus RH nu by kT. So from this, we'll get N1 is equal to N0 into e power minus h nu by kT, and N2 is equal to N0 e to the power of minus 2h nu by kT. Therefore, we'll get N1 by N2 is equal to, so this N0 N0 gets cancelled. Here, this will become e power h nu by kT. So substituting this N1 by N2 in equation 5, we'll get rho of nu is equal to A21 by B21 whole by B12 by B21 into e power h nu by kt minus 1. So this is our equation 6. And we know that from Planck's radiation law, rho of nu is equal to 8 pi h nu cube by c cube into e to the power of h nu by kt minus 1. So this is the density of radiation which is given by Max Planck. So comparing these two equations, that is our equation 6 with the Planck's radiation law, will get, as here the exponential part e power h nu by kt is having the coefficient b12 by b21 in equation 6. But in Planck radiation law, the coefficient is 1. So therefore, on comparing these two equations, we'll get B12 by B21 equal to 1. So this is our Einstein's first relation. And second equation is whatever the remaining part is there. So this part is equal to the remaining part. So that is A21 by B21 equal to 8 pi h nu cube by c cube. So this is the second Einstein relation. So by using these two relations, we can identify the medium which is having the stimulated emission process. This B12 by B21, B12 means it is the rate of stimulated absorption, whereas B21 is rate of stimulated emission. So the ratio of the stimulated absorption to the stimulated emission is equal to 1. That means whatever the absorption process is going on, if all the atoms are coming down stimulatedly, then in that medium is suitable for the laser transition. The second relation gives the relation between the stimulated emission and the frequency. So here nu cube is there. So here our B21 is the rate of stimulated emission. So to get more stimulated emission in a laser medium, which frequency is suitable? We can get by this second Einstein relation. Here B12 by B21 is equal to 1 is the first Einstein relation. A21 by B21 is equal to 8 pi h nu cube by c cube is the second Einstein relation. Whereas A21, B21 and B12 are the Einstein coefficients.